Okay, so the last video I got cut short in time a little bit, so I want to back up a second. That we know that the acceleration is equal to F over m, and we know for a spring system that that force is equal to kx over m. So what we end up getting is that the acceleration is equal to the, and this is a restoring force, so minus km times the position. And the position, as we saw, is this a cosine 2 pi t over times t. So we have minus k over m times a cosine 2 pi over the period times the time. And some kind of neat things that when we're talking about this, okay, if we go up here, that if our time is equal to the period, so in other words, these two are equal, then we have cosine of 2 pi, and cosine of 2 pi is equal to 1. So all this is saying is that when the period, the time is equal to the period, if we have 1, the position is at the amplitude. So all it means is saying that it's over here. So kind of neat when the math makes sense of what we're looking at. So let's just kind of do a quick refresher of sine and cosine. So anything that is a sine function starts off with 0 amplitude and oscillates back and forth. Anything with a cosine starts off at 1 and oscillates 1 full cycle, like that. So with that in mind, let's take a look at the initial conditions. So what we're saying is that the original position is at the positive amplitude, is one case. The initial position is in the center, so x equals 0. Okay, and notice that the velocity is at a maximum at that point. And then the third position is when the position is at the other side, the other amplitude, so on the far side. So oscillating back and forth. So if we think of the shape for the position time graph, what we end up thinking about is that when it's at its furthest position, that it's oscillating back between a and negative a, so those are the boundaries, and it's going to start off with a. Sometime later it's going to be at in between, sometime later it's going to be at negative a, then back to 0, and then back to positive a. So this is one complete cycle. So I'm going to connect those points. And you will see that this is following what a cosine graph looks like. So if I go back up here, we can replace any one of these trig functions with either sine or cosine depending upon what the initial conditions are. Because essentially they are the same, just the only thing that's different is basically the wave is shifted by a quarter of a wavelength. Okay, sine and cosine is just altered by this 90 degrees, okay, which is 1/4 of the wavelength. So the equation that I can write for this is a times cosine, since it matches this graph right here, times the 2 pi t over times t. Now I'm going to actually just write this 2 pi over t in for omega. So it just looks a little cleaner. So this is just a cosine omega times t. And just realize that you can replace this omega with 2 pi over the period at any time. Now, if we make use of the idea that the velocity versus time graph is the slope, what I'm going to do is I'm going to look at a bunch of tangent lines as we did before and plot points. So at the first, and I'm going to try to make these line up. So when this is right around here, the velocity is at a maximum in the negative direction. Here we have some flat parts, so I'll put a 0 in there and then a 0 in here. And then there's a positive extreme right there. And so this is oscillating back between Vmax, I'm just going to write V sub m, and negative V sub m. And we'll connect these like so. And you can see that this is actually not a sine graph, but this is actually a minus sine graph. Okay, so this is actually minus V max times and sine of omega t. Okay, so that's just what we have up here. Okay, where we replace 2 pi over t, okay, for the omega. And what we didn't talk about is the third graph, okay, but we do know that the acceleration is the slope of my velocity. So if I plot some points in here, what we end up getting is that we start off with not a positive value, we start off with a negative value, and I'll talk about what that that boundary is. And then we go to a 0 point, and then a maximum positive, then back to a 0 point, and then to a extreme negative. And so we see a graph that looks something like that. So this is actually not cosine, this is minus cosine of omega t. And what are these boundaries? Well, if we go back up here, the coefficient in front of here is km times a. So this is bouncing back and forth between minus km times a to positive km times a. Okay, so that's our value. So these don't have the same amplitudes, okay, between these three, but they are. So this is minus k over m times a. All right, so how is this varying for when it's in the middle? Well, essentially we're going to play the same game just with a different starting graph. That the velocity starts off at a maximum when the position's at 0, so it starts off at 0. And let's say that it's going to the positive side first, so I could choose whether it goes positive or negative first. I'm going to choose positive. So sometime later it's at a positive graph, then it comes back to the center, then goes to negative amplitude, so negative a to positive a, and then back to center. So we get not a cosine function, but we get a sine function. So this is a sine omega t. And then we play the same game with the slopes. In blue here, positive, 0, negative, 0, positive. So we start off with a positive number, then go to a 0, then go to a negative number, and then back to 0, and then back to the positive. And draw some nice smooth curve in there, something like so. And what we end up seeing is that it's actually a positive cosine. So this will be V max times cosine omega t. Notice that there is no negative here anymore because we're just starting at a positive value. And the extremes, the boundaries still stay the same. That this is V max and this is minus V max. Okay, and then for the last graph, the acceleration time, we go from 0 to negative to 0 to positive to 0. So we have 0, we have a negative value, we have back to 0, we have a positive value, and then back to 0. So draw a nice smooth curve in connecting those points. And so we see that this is not sine, but this is actually minus sine. So this is minus k over m times a times sine of omega t. Okay, and then the last graph, back here in red, is basically going to be a reverse of this, that we go from negative a to 0 to positive a, then back to 0, and then back to negative a. Draw a nice smooth curve, and then we draw in our slopes. We have 0 slope, positive slope, 0 slope, negative slope, 0 slope, and then connect my points, so 0 to a positive, back to 0. I'm trying to line these up here. Okay, that's a little shifted. And then back to negative, and then back to 0. And we draw a nice smooth curve in for that. Now notice this. Hey, look at that. This is our original sine function. Okay, and notice it's positive. So this is actually going to be positive V max times sine of omega t. And I'm sorry, we skipped over this. This is not a cosine graph, but this is actually a negative cosine graph. So when the initial condition is at the negative amplitude, we start off with a negative a cosine omega t. Go figure. Okay, and then for the acceleration graph, our last graph, we have a positive, 0, negative, 0, positive. So we start off with a positive, we go to a 0, we go then back to a negative value, then back to a 0, and then to a positive value. And then connect those points. And so this, of course, is a positive. So this is k over m times a times cosine of omega t. And those are our three conditions. Okay, and so I'd like you to try this one out. Okay, and I'll tell you this, that you do have to find the period first. Okay, so you have to find the period based on the fact that the period is equal to 2 pi times radical m over k. And then once you find that period, then you can use this velocity equation for when x is at the middle part. So this is going to be the Vmax times cosine of omega t, and it'd be useful to substitute that omega, so Vmax times cosine, as 2 pi over the period that you found in step 1 times the t, so when t is 1 second. Okay, and we know that when x is 0, this is actually your maximum speed. Okay, so we'll check up on these when you guys get back, and we'll have a great day, and we will see you soon. All right, take care. Bye-bye.